All right, today we are going to talk about something that's related to the trailer that we just played about Super Mario. And we play a music from Coco just before the lecture, and some of you probably know the reason why, right? So I think on Friday it's the Mexicans. How to pronounce that? Okay, you guys got it. Okay, so sometimes I feel like culturally, no matter which country you are from, there are a lot of similarities there, right? Like in a like, well, actually, I did a little bit of research regarding where Halloween comes from. It's actually, I think, is in the Middle Age in Europe. Then they started that, right? And for Mexico, I don't know how long it lasts, but they also have this kind of day that like your ancestors would come back, right? And like in Chinese culture, there's also a month like that. So sometimes I feel in the past I was thinking about like if I want to die, then I would probably pick somewhere in the greater like Chinese culture area because at least when I die, I still have a month to come back, right? But in a Western culture, it's just one day, right? But then today, this morning, I changed my mind because I feel like, okay, the reason why they can stay there for longer is probably because it's a better world in the Western culture, so they don't really want to come back, probably. But anyway, enjoy your great night tonight. Be safe, stay safe, prepare your costume. I saw some of you have a great costume just now, which is, no, he took it off. So no worries. But most importantly, don't forget we have a winter next Tuesday, and what we teach today is going to be covered. So I know you missed this guy for a long time. We haven't talked about him for a long time, right? John von Neumann. So in the past, we have been like really focusing on the memory part, and but don't forget, right? After we address the memory problem, it's about the processor, right? After we deal with the fetching problem or the data access problem, everything goes back to the processor, how we can run all the tasks that we need to accomplish in the processor efficiently. So that would be the lecture we are going to starting for the next series of computer architecture. But let's remind ourselves, essentially, what is a processor? So remember, the processor is a collection of functional units that helps us to complete the instructions, the tasks, the computation tasks, or data manipulation tasks that we want. So basically, the processor, from a high-level perspective, let's forget about all the pipelines, let's forget about all the data path elements. From the very high-level perspective, it's just a collection of functional units to perform each instruction. So if you really want, you can actually like implement a processor with one dedicated functional units for one dedicated instruction. That will also work, right? However, you read a lot of like optimization of the data path. It's all about how can we save the cost of implementing hardware. So, but let's set that aside. Essentially, what a processor is just a collection of functional units that allow us to execute instructions. And to make programmers easier to control the processor, we start to have the abstraction called instruction set architecture that defines a set of basic features that each processor under the same contract should follow. So the most noticeable instruction set architectures for now, apparently x86, Intel AMD processors use that. And another one, which is increasingly important, called ARM. So like Apple or Qualcomm or NVIDIA's general purpose processors, they all use ARM architecture. And there is another one, what John Tennessee and Debbie Patterson, they propose, and is featuring an open source nature, open architecture nature, so everyone can get a license with really cheap price, because one of the big problem with ARM is because their license fee is really expensive. And if you are paying attention to what happened right now is that they are currently trying to charge Qualcomm a lot more by like raising a lawsuit on that, right? So a lot of people might want to go to RISC-V because that's another open architecture that's cheaper. But when we talk about this like RISC-V or ARM or x86, it's only at the level of instruction set architecture. So that's why even though like Apple has ARM processor, NVIDIA has ARM processor, Qualcomm has ARM processors. However, all their ARM processors has very different performance characteristics. And that's the same between Intel and AMD processors. So, and the good thing about having this abstraction is because as a programmer, right now we don't have to worry about which processor we are dealing with. So do you find the same story again and again? Right? Like we invented virtual memory, so programmer doesn't have to worry about how many how many memory you have. And right now in a processor, we also create the abstraction that as long as this is the hardware support this instruction set architecture, your program will run, right? No matter what processor you are using. So that's the instruction set architecture. So the programming language runtime or the compiler will generate instructions based on that. So before we dive into the detail of this lecture, I want you to share a few things with us, the rest of the group. And yesterday I was thinking about this question too. Where do you typically go to lunch on campus if you are short on time? Why? Okay, Hunter, what do you think?
You go to like one of the convenience stores.
Convenience store?
Yeah, you pick up one of those
Sandwich
and a bag of chips, and then you can eat on the way.
Okay, you can do it on the way. Okay, convenience store. That's one of the option. What else? Yeah.
I'd like to go to the Pandas on the hub.
Okay, Panda Express. Why?
It's cheap and
Cheap? Is it really cheap?
it's relatively cheap.
Okay, what else? It's cheap and what else?
What else? Bring some food on my own.
Okay, what else?
Probably the same as Scotty's like at the hub.
The Scotty, but do they have good food?
It's just convenience store.
It's just convenience store. Okay. Okay, what else? What else do you guys have? Kelly, what do you typically would eat?
I bring my lunch because the lines are too long and I don't have time to wait.
The lines are too long. Yes, that's always a problem. Right, what else? Okay, well, I will share with mine later for you. But you know, like, before we start, I want you to think about this question. let's take a look. Okay, so we have definitely some debate on B and C that's worth going on. So why don't you guys go ahead and talk to your friends for another 90 seconds, and let's check the answer later. All right, let's take a look. Okay. So, this is like the election. If you haven't voted, you should go vote. Okay, I think you can do early vote. So, I want to hear both sides. The red, I didn't do this intentionally, but apparently we have A as red, B as blue, right? So for the red part, what do you guys think? Oh, actually, like B and C, right?
Yeah.
For B, what do you guys think? Okay, Hunter.
Okay, so my group discussed that the operations, the shift, and the subtraction is faster than the multiplication option.
Uh-huh.
But we're also considering the fact that since it has two data reads, that overhead might lead to a longer execution time than just the multiplication.
Uh-huh.
But we rationale that since they're actually the same index, right? The data is going to be in the cache, so it's not going to. So like.
Mm-hmm.
So the slight extra overhead is not going to be as bad as the multiplication operation.
Okay, so you see so which one do you pick?
We think it's B.
You think it's B?
I mean, we think the option C, the B is faster because the CPI is lower.
Okay, so that means you choose C, right? Because
Correct.
what you explain, I feel like, okay, that sounds like C.
No,
Okay.
it's like,
Yeah, B is faster because you think the CPI is lower.
Yeah.
Okay, what else?
I think it's C because
You think it's C?
in the right hand side, we shift the index by 4 and we shift by 4 then subtract some number, right?
Okay.
So it's two instructions.
Uh-huh.
In left hand side, it's a multiply operation.
Uh-huh.
It takes longer.
Okay, multiplication is longer, so you think it should be B, even though you should think version B is faster. Okay, you pick B not just because you are in California.
No.
Okay.
Wait, what I was thinking was that it's.
You wear red.
Yeah, I'm wearing red.
Okay. What do you think?
I'm basically B version A is faster than because the IC is lower
Mm-hmm.
because there's no optimization, so we're assuming everything's going to be read from the stack directly anytime you access the data. So it would be from the cache instead of the register directly.
Right,
So in
that is
sense,
true.
I think the multiplication would already be in the register, so then it would be a little bit faster in that sense. So that's what I was thinking that, and as well as less instructions in general.
Okay.
Since like there's two instructions for the bitwise and then the minus rather than just the multiplication.
Okay, so I think all of you have some ideas about what's going on in these pieces of code, right? But if we put everything together, what the real result looks like. So let's run it. Okay, miss programming. Where is it? Okay, here we go. Let me run it. Okay, so this is the code that we have, right? The left-hand side is the multiplication. The right-hand side is the shift. And let's run it and see what's going on. So to be fair, I run each of them 5 times, and then I will generate a table. So in the first run, apparently the left-hand side is faster. The second run, the left-hand side is also faster. The third run, the left-hand side is still faster. The fourth run, the left-hand side is going even faster. The fifth time, okay, right? So if you see that, right, what tells you? So instruction count on the MUL version is lower. The CPI on the MUL version is higher. But that put together, end up, the instruction count wins. Right? The instruction count matters more. So why is that? Why is that? That's something we are going to talk about in this lecture. And another thing, I don't know if you remember, a lot of people think, okay, if we are doing a swap as a performance programmer, I should do things like the B version. It's just one line of code, so I'm really a superior programmer, right? So if you want to do that, and I hope you still remember the demo, if you don't remember that, one thing that I can show you is that I put that swap in a flip array program, which you can find the algorithm on LeetCode if you want. I believe this is one of the questions. And let me run it again so that you can, because previously we were doing it on quicksort, and there are a lot of factors, not just swapping on quicksort, so it's hard to see the benefit of that, right? But right now, if you do it on flip array, you can easily see the effectiveness of this 2 versions of swapping. And you can see all the version A, they are consistently faster than version B, right? So it tells you that, okay, the right-hand side is not better, even though it sounds like more, it seems more professional, right? And you also remember this, right? We talk about, okay, we have a sort in the very beginning to change the order of my data array. However, that would give me like 4 times speed up over the one without sorting. Why are those? Why are those? We are going to gradually answer those questions in the following lectures, so don't miss the next 2 weeks. So today we are going to talk about what's the concept of a processor. We are going to talk about pipeline processor, and we are going to talk about pipeline hazard and how to deal with one of the hazards. So first of all, the life of an instruction. So can you guys remind me? We actually have this on the first slide, right? Like, what's the life of an instruction instance? What's the life of an instruction instance? What was the first? Fetch instruction. Okay, that's the beginning. And after that, what's the next thing? Decoding instruction. What does that mean by decoding?
Figure out each bit what is doing what.
Okay, figure out what the instruction wants us to do. What's the next? Can we execution? Can we execute after we decode? Okay, so another thing, right, you have to do is you have to prepare the source registers values in front of your targeting ALU before you can execute. You have to get everything ready. That's also part of the decoding stage, right? Decoding stage is easy to forget. A lot of people just read it just read it by name. So you guys think about, okay, after I know what instruction wants us to do, that's good enough. But don't forget, your ALU also needs input. Your data memory access unit also needs input. Who prepares those input? That's also should be done in the instruction decode stage. And when we execute, what do you mean by execute? What do you mean by execute?
Well, it can be some computation, some control actions.
Okay, some computation, some control actions. Can you elaborate more about on the control actions?
Control, for example, we want to jump to another location.
Oh, you want to jump to another location, so what should we do at that time?
We will set the PC counter to another.
Okay, you have to do that kind of stuff. Okay, what else?
The instruction is either going to load from memory, store to memory, or it's going to update a register value.
Okay, so if I have that kind of instruction, what are the other things that I have to do before I can access memory? You calculate the memory location. So actually, execution stage is not just a single ALU operation. There will be many different types of operations depending on what instructions you want to perform. So that's why I'm saying for each different instruction, you could have a different functional unit for it if you really want to implement that kind of processor. So for example, you may have integer instructions, then you will have an integer ALU. If you have floating point instruction, you will have floating point ALU. And sometimes if you have a conditional branch, you need to determine if it's taken, not taken, and calculate the target address, right? And for memory instruction, you need to determine the effective address of data memory access. So, and then you can access data memory if you want, right? And finally, after you have done all the operations, you want the outcome to be propagated to the upcoming execution sequence. So you need to present your value in a register before the next instruction can go. And finally, we want to keep fetching instruction, right? So we also need to update the program counter depending on if your branch is taken or not taken, right? If your branch is taken, that means we are going to set the branch, the PC to the branch target address. And if not, we just advance to the next instruction. And in some instruction set architecture is PC plus 4, but for x86, that's not a determinant number, right? So with that, you can imagine, first of all, we want to do instruction fetch, right? Where are we fetching from? Remember from the last lecture, right? Everything must be from the cache. So we will have a cache, right? And that's something we typically have on the processor now. And you need to have an instruction fetch unit. And for the instruction fetch unit, where are we fetching the instruction from is determined by the current value of a spatial register called program counter. So the program counter would determine where are we going to fetch the instruction from. So program counter is essentially a pointer to a location in the instruction memory. And that instruction memory location is also cached by your L1 cache. And then after we fetch the instruction, in your processor, there will be somewhere decoding that instruction. And after we decode, we would be able to know what register values should we precharge so that the following functional units that are performing the corresponding operations can leverage that register values to perform their calculation. And depending on what kind of instructions you have, there may be several different types of ALU corresponding. And typically, we would say there will be arithmetic logic unit for simple operations, complex operations, and address generation and memory access for the data memory pipeline. And then there will be another one dealing with the branch and jump instruction. And after you are done, so if you have a data memory access instruction, you will have to access data from the L1 cache again. And after you are done, if it's a branch instruction, you might need to update the PC. If it's other instructions, you will have to update the register values. So if we want to perform instruction, the simplest design would say, hey, let's just do one thing at a time, right? That's typically us, right? Like sometimes I feel like, like I'm a person that I'm dedicated to just one thing at a time. So one thing that would happen to me is that I have to finish the text from the beginning to the end before I can start the next, right? you can imagine you are go to a shop, like especially most of the time, like coffee shop, right? They would like just serve one customer at a time, right? And that's typical, that's the simplest design of the processor. So only after the first instruction, write back, return back, and update the register values and the PC, we can fetch the next instruction. And before we finish the next the instruction, we cannot execute the next instruction. So that's, you can imagine with that, right? An instruction execution sequence is pretty much like this, right? You finish all the tasks of an instruction, and then you go to the next, right? But as you can imagine, this is very inefficient, right? The throughput of this shop is definitely not going to be great. So most modern processors, they incorporate the idea of pipelining. So what is pipelining? So the most famous pipeline is probably this, right? Something like this. Okay, so, but what is pipelining in hardware? So pipelining is, we partition your tasks into several different stages. And different parts of the processor can work on different instructions at different stage at the same time. So it's still the same processor, but we partition the processor into several segments. Each segment is potentially possible to work on an instruction for the task it wants for that segment. That's the basic idea of pipelining. So in that case, right, you can imagine a processor could have the instruction fetch unit working on one instruction, the execution unit working on another instruction, and in the meantime, data memory access, write back for another instruction, right? So, and the clock signal will control and synchronize the beginning and the end of each part of the work. And a pipeline register will be added to buffer the temporary result from each stage of the execution. So that's the basic idea of pipelining. So you can imagine, here's the idea of pipelining. So first of all, we say there's a clock, right? The clock controls the operation of each different parts. So you add a few pipeline registers like the yellows here. So what happened is that, okay, let's say I pipeline the processor into 5 different stages, and they are all controlled by the same clock. So in the first clock, when the first clock signal comes in, right, I can have the first stage occupied by the red instruction. And during a clock cycle, the red instruction would only make progress that's sufficient enough for the first stage. So in the next clock cycle, the second stage of the processor can pull up the pipeline register content to know where are we left over from. And for the second stage to continue work, make progress on a red instruction. But in the meantime, the first stage of the processor are already freed up. So we can see the orange comes in. So gradually, you can see if we have 5 cycles later, then every pipeline stage is occupied by one instruction, and each instruction is working on a different type of task for different instructions. So if you cannot coherent what's pipelining, let me share one of my favorite plays. If I'm short on time, that's actually Subway. So for Subway, it really implements pipelining, right? Can you imagine that, right? Like, well, well-trained Subway. What happened? You know, okay, so here's the thing, because like, we have a lot of student workers on campus, right? So in the beginning of every quarter, that's the time I feel Subway the least efficient, because, you know, once in a while, the attendee has to ask the manager, oh, what to do with this? He wants to order that. I don't know how to do that, right? But mostly when people are well-trained, this is what happened, right? First of all, what's the first question? When you step in the line, right, and then the first attendee would ask, what kind of bread, right? And I would typically say bread, flat bread. Do you want to toast it? Sure. Okay. And then what kind of protein, right? And in the meantime, when people ask you the people who ask you about the protein is a different person who asks you about the thread. And if you can overhear, you can also hear what kind of bread, what kind of protein, right? Veggies, right? So you have different stages, and you can have multiple people working on this like you can have multiple customers going through that line, and finally the register, right? So Subway is in data pipeline. So if you are still unaware about pipelining after the lecture, you can definitely go to Subway, right? So they should definitely pay me for like advertisement, right? Okay, so that's pipe. So let's see how pipeline execution will help us. So on a processor, what happened is that, okay, I insert those gray lines, which are the pipeline registers. So whenever the first clock cycle, instead of having the instruction goes all the way to the end, within this clock cycle, the instruction only needs to finish its fetch. And then the next cycle time, the blue one comes in, and the red one, the purple one would go to the instruction decode, right? And then in the next clock cycle, the purple one goes to execution, the blue one goes to decode, the green one goes to fetch, right? So three of them are now in a processor pipeline. In the next cycle, the first instruction write back its value to register, and the blue instruction is now occupying the LU, and the green instruction is using the decoding unit, and we are fetching the orange instruction. Question?
Yes, we have multiple stages, and so we have multiple instructions.
Mm-hmm.
Within the same time.
What?
So like, what the value of program counter actually belongs
So the
to?
program counter, as we said, right, is telling the instruction fetch unit what to fetch. So it's always pointing to the instruction that the instruction fetch unit should be fetching. Okay? So that's the basic idea of pipeline execution. So in this way, you can see that the good thing about this pipeline approach, definitely, for each clock cycle, every instruction only to move a small step, right? So you can imagine what the biggest benefit is that your clock rate can go really high if you partition the pipeline into multiple stages, right? And the second thing, which we can also tell, is from this pipeline diagram, if you took your undergrad computer architecture, you probably had this experience for a long time. But one key takeaway from this kind of pipeline diagram is after a certain point, if you observe the output of the processor, every cycle, we are producing the outcome of from an instruction, right? So you have shorter cycle time, your CT is lower, and you still maintain the same CPI. What does that mean? Your cycle time is shorter, your CPI is still the same. What does that mean? You have more instruction per second. What does that mean? Your performance is better, right? So, but is it always the case, right? So let's take a look of these pieces of a code and see, is it often the case that we can achieve the target performance gain as we want?
the results produced after the
I mean, after the instruction is done. All right, let's take a look. Okay, so definitely this is a question we need a lot of discussion. So why don't you guys go ahead and discuss with your friend for another 90 seconds. Oops.
That's back to back.
And another one is the jump instruction because all the stuff you were doing, like it was going down, you gotta go jump back up. So I think
We have those registers in between each phase of the pipeline. So after though the instruction may not be completed yet, that result should still be available.
Yes, but you have to implement some jumps.
Okay, let's take a look. Okay, so most of you think it's either B or C. Okay, can some of you share your thoughts with us? Okay, Joshua.
The jump instruction could cause a problem because we might not be able to predict accurately the jump when it's going to jump and when it's not going to jump. So that could lead to a flush or something like that.
So you don't know if we want to jump or not.
Yes.
So that's definitely one issue.
Yeah. And then we were also discussing the issue of instructions 1 and 3, how you have a right to, and then.
So here they are writing to EAX.
But then it's being accessed and add, and that could be a problem. But then I was thinking it shouldn't be a problem because we have those registers in between the various phases. So the data should.
You have register between various phases?
The pipeline registers.
But shouldn't we get this value before we can count this correctly?
But even if the instruction isn't completed for instruction 1, the value should still be available, no?
Should still be available. Okay, let's talk about this later. What else?
another one our group noticed was the move instruction, because you're taking like the move and then you're immediately using it, and so that you wouldn't have access to that time. So that's one.
Okay, so this instruction would need this value.
Yeah, we don't.
Okay, so that's one.
And then another one was the add queue and compare queue, because we need the
RDI
value, and we don't have it yet.
We don't have it yet. Okay, so that's why the big picture of the processing is really important. That's why remembering things are so important, right? So, a lot of cases, A lot of cases. People want to avoid hard problems. People want to avoid like complicated steps. But how do we address this question in particular? Unavoidably, you have to draw the pipeline diagram and see what's going on. Okay, so in the first cycle, we would definitely not having trouble fetching the first instruction, right? And since this instruction is not a branch instruction, so we are 100% for sure the next instruction should be the one being executed if we don't have any exception, correct? Right? So the next cycle, we can definitely push the first instruction to decode and fetch the next instruction. Now, at the third cycle, are we safe to continuously fetching and decoding and executing? Yeah, we can. That's not a problem, right? Because right now, no one is using that ALU, that the first instruction one. And the second instruction, we haven't even figured out what it's doing, right? And if we are doing the second instruction, at least we know it's not a branch instruction, so we can continue, right? Okay, so now, how about the next cycle? There's no memory access
in the first one.
in the first one.
Right? Then you move on to the execution change to find the register.
So we can write back for the first instruction and we can calculate the effective address for the second instruction and we can perform the decode for the third instruction and keep fetching. How about the next cycle?
Then you have a problem.
This is where we have a problem.
Okay, we have problem. What kind of problem?
Well, EX is not written back yet, so we can't do the execution because we don't have the value.
We can't do that. Yeah.
Okay. Is that the only thing that's problematic? Is it really okay to do things at this cycle? Mm-hmm. Mm-hmm. Okay, you got it. Both instruction 1 and 3, they are attempting to access the same register at the same cycle. Did we ever mention that's already added into our hardware? That's a remedy of that, right? Yeah, and the thing is, right now, we don't have any solution for this yet, right? The story hasn't been there, right? So, okay, so one of the things that's troublesome right now is we don't have a way to deal with that situation, right? Who goes first? Who goes later? Again, even though, okay, so one thing that I think some of you asked on Discord, and in the very beginning, I was like thinking about that. That was the confusion, but I realized there's one thing, because I noticed that problem, so when I designed that reading quiz question, I was wording carefully. I mean, at the same time. So even though with that optimization you guys mentioned, it's still not at the same time. One has to go first, the other has to go later, and we have to carefully partition the cycle into half. So it's technically two different cycles. So none of the two instructions can share the same hardware at the same time. At the same time, they can't. So we have to address this, right? So this is definitely something. What else? So when we go to the next cycle, let's forego this, right? And then if we go to the next, what's going on? So here's the thing, right? Some of you pointed that out. Here, when I decode, I'm getting a value that was previously in the register, not the value I want, right? And the other thing, we have only one memory unit, right? The second instruction wants to access cache, but the first instruction also wants to fetch from cache. There's a conflict here, right? So this is not going to work, right? And the data that you got in ECX is actually not right at this moment, right? So that's a problem that some of you pointed out, right? So right now, like at least 1 and 3, 2 and 4, 2 and 5, 2 and 3, that's already 3, right? Let's keep going. At this point, okay, two of the instruction wants to write back at the same time. Is it possible? No. We only have one set of pipeline register, right? So none of the two instructions can go to the same pipeline stage at the same time. So this is not going to happen, right? And keep going, right? Okay. So again, we want to compare RDI. But here, when I decode this instruction, the RDI is not generated yet. So I cannot get the right value of RDI, right? Right? And also, some of you pointed out, for this jump instruction, I don't know what's the next to do. So all of them, right? You can figure out that, okay, although pipeline sounds very ideal, it's almost impossible to have a perfect pipelining in a code snippet like this, right? So that's actually a problem that we want to address. But in summary, so far we learned pipelining is a way to shorter the cycle time, improve the throughput. However, the theoretical CPI should remain the same, but it's very difficult to achieve. And why is that? Because we have 3 different types of pipeline hazard. The first type of hazard is called structural hazard. Structural hazard means that we have a conflict in one of the resources that 2 instructions are competing with just one piece of hardware. That could be one pipeline stage, that could be one functional unit, that could be memory. The second type is control hazard. It means we simply don't know what's the next instruction. And remember, one key thing that could keep the pipeline keep generating the output is that you need to continuously having inputs. If you only have if you keep outputting, your pipeline is going to be empty out, right? So control hazard is also one of the key things that needs to be addressed to keep the pipeline filled. The third type is data hazard. So sometimes, yes, I do have the instruction, I decode it. However, if you want me to keep going, I'm not going to generate the desired result from a programmer's perspective. I can generate some result from a mediocre register value that doesn't mean anything to your execution outcome. But that's not what you want. That's called data hazard, is because an instruction, the value, it really depends. It's still being generated in a pipeline or is still not propagate to the source register of another instruction. That's called data hazard. So here is my showing about hazard. So like this morning, some of you had a meeting with me and he got late. I got one of the reasons probably hard to find a parking spot, right? And sometimes once a while, when you find a parking spot, you are really excited. Oh, there's a spot. Then you figure out, oh, there's a motorcycle there, right? So even though, right? So here's the thing, even though a motorcycle is shorter, even though it's small, because it's occupying that parking spot, So you cannot use that spot. That's a structural hazard, right? You and a motorcycle, you both want to use that parking spot, but it's not possible, right? That's called structural hazard. The second type of hazard is called control hazard. I don't know how many of you watch baseball game, but you must oftentimes see this, right? Like some people try to challenge a decision. So the game cannot keep going until we have this decision resolved, right? That's called control hazard. And this is probably something you experience the most amount of time, right? Okay, right now, I want to do things. I'm really eager to do something. I want to watch a movie. I want to work on my assignment on the data hub. I just couldn't because it's loading, right? Your data, the stuff you want is just not ready yet. So there's nothing you can do, right? So those are the three types of pipeline hazard. So now, based on this, can you tell me how many hazards here are considered as data hazards? All right. Okay, so most of you think it's either C or D. So why don't you talk to your friends for another 90 seconds and let us know what you think afterwards. All right, let's take a look. Okay, now most of you think it's C. What are the two that you guys have in mind? What are the two? Which one? Okay, so first of all, right, this is like a structural hazard, right? Because, for example, right now, both of them want to fetch from memory, right, or access memory. For this one, it's also a structural hazard because we all want to access EAX, right? And this is a control hazard because we cannot determine, right? And two of them, and this one is a data hazard because data not in ready in there yet, right? And this one is also data hazard because data not in RDI yet, right? And 2 instructions on the same stage is definitely a structural hazard, right? So now you understand that's 3 basic types of hazard. Can you answer me why the left-hand side is better? Oops. All right, let's take a look. Okay, after discussion, more of you think the answer is B, data hazard. Oh, it's not discussion, shoot. Okay, so why is it data hazard? Can some of you share that thought with me? Why do you think it's data hazard?
Each result in the second post-it directly depends on the next one. So the result of the first line of code.
Okay. Right, so if you do an analysis, right, for the left-hand side, although it seems stupid in some sense, right, but here, temp is depending on A, and now A is depending on B, right? So these 2 instructions, they don't have any dependency, right? And this instruction is depending on this, right? So you have 2 separate dependency chains. However, for this one, the A comes from B, and then B depends on A, and A depends on B again. So they all chain up together as a single dependency chain. And from what you just learned, right, if you have data access instruction or computation back to back, you are more likely to have data hazard. So that's why, hello, why all the batteries are, you know, sometimes the budget cut shouldn't affect the battery. Maybe we shouldn't bolt so early, right? Oh, there's no battery. Okay, so yeah, so for this one, it's because of the data hazard, right? So a lot of cases, programmers are not aware of the pipeline processor design. So they write code that they think that are fancy. However, for this case, it's definitely something that lack of consideration. So right now we know we have 3 different types of hazard, and that's why sometimes we do have trouble not seeing the expected program performance, even though we think we are doing the right thing, right? So the universal solution, so first of all, right, if you want to do things, the first thing is always make it right before make it fast, right? So that's why make it right is so important. So that's why in your programming assignment, if your answer is not right at all, even though you get speed up, we are not going to give you any scores. because make it right is the most important thing. So the universal solution to make it right is just stall, right? So for example, right now at this cycle, if we can just wait, let other instructions after the problematic instruction wait, then everything would go well. So for example, if instruction 3 is waiting on instruction 2's outcome, then everyone else just wait at the same place where you are, right? Only the second instruction can make progress, right? And then once you have done that, the next cycle, okay, it's still not written back yet, right? So we have to wait for one more. And then after this waiting, right, we can finally decode the right register source values. And then you can continue, right? And then whenever you meet this kind of cases, you just wait. But apparently, is this something you want? Do you want to wait? No, right? We don't want to wait because like for this code example, we have to spend 4 additional cycles for this sequence of instructions, which is not something we want. So we need more clever solutions to address those hazards. And let's start with structural hazards. So the first type of structural hazard that we just discovered is what if we have conflict between instruction decode and write back stage? As we mentioned, instruction decode stage want to read values and write back stage want to write values. They could be the same register, right? So if that's the case, the solution we have is write early, read late. So why is write given a higher priority? It's because typically the later instruction, which depends on the same register value, tends to read, right? So, and you want that value. So if you allow write early, read late, if you give priority to write, at least you can reduce the wait, right? And also, registers, they are very fast. So a possible way of optimizing it is that we play some trick in a hardware design. In a rising age, we perform the write. And in a falling age, we perform the read. So although some of you would think, okay, isn't that reading and writing at the same time? It's not. It's writing at the first half of the cycle and reading at the second half of the cycle. So it's still at different timing, but that timing happened to be at the same cycle. So with that, what will happen is that, okay, right now for this sequence of instruction, when I have this one writing back, right, I can also allow the second instruction to get the EAX it wants, right? So that can continue, right? So that's the first fix. And the second fix, which is even more problematic, right? We have trouble fetching and accessing data at the same time, right? Do you have any idea how to fix that? And actually, you have seen that solution everywhere already. Yes, right? Split L1 cache. I kind of avoid saying this in the memory section because I think it's too early to bring that up. But a lot of you should be aware. Although I keep saying like L1 cache, in the experiments, in assignment, I just simplify everything, assume there's only data cache, right? However, in fact, in real hardware, if you pay attention, at the level of L1, there's always IL1 cache and DL1 cache. Why is that? Because instruction fetch and data access, we cannot have them conflict with each other to create structural hazard. So that's why every processor has a split L1 design. That's the main reason why we have a split L1 design. And the other potential reason is also because for code, it's typically loop and falls through in basic blocks. So it's very easy to predict, and their size are typically small. So have a separate cache would maintain very high cache miss rate for the code at least. And you don't actually need to access data for every instruction, but you definitely want to access instruction for every instruction. So keeping the instruction cache with high hit rate is very important, very critical to performance. So that's another reason why we advocate the split design in L1 cache. So that explains why I see split L1 design all the time. But at the L2 level, because it's not directly interfacing with the processor pipeline, so we are okay to have a combined unit. Okay, so now with this revision, you can imagine this is our pipeline, and I have like cut the instruction cache in half. So now, the next question is that, okay, both instructions. So now, if I have a problem of like both, So if I have two instructions that needs to, so for example, right now I have instruction 2 and instruction 3. They are both done at this moment, right? They're both done at this moment, right? So what happened? You still need the next instruction to stall, right, to prevent a problem. Or another thing, which could potentially be a structural hazard is, what if I have back-to-back memory instruction? So far we say, if we have a split L1 cache, right, that will keep the instruction fetching unit smooth. However, most of the time, your memory latencies are longer, right? So you need more cycles to get the data, right? So in this thing, if you only have one data memory access unit, it's still not going to work out. Agree? So what should we be doing? So the next thing, right, is we have also make the cache non-blocking. So right now we are talking about the concept of blocking cache is that the cache can only serve one request at any time. Until the request finishes, we cannot serve the next request. So similar idea as pipelining, right? Similar idea as pipelining is that the pipelining partitions the hardware into different units. So one thing that we can do with the caching is that we set up a queue in the caching unit. So the cache can consistently accept requests. And as long as the requests are not conflicting with each other on the same accessing unit, which we call bank. A bank is a collection of chips, right? As long as they are not conflicting in banks, they can be served concurrently. So multi-bank and non-blocking cache would allow the memory instructions to also be pipelined so that we can consistently executing memory instructions as well without having to wait all the memory instructions to finish. So you can imagine if you are lucky enough, you could have request 1 going to bank 1 for multiple cycles, and starting the next cycle, you can access bank 2 and then bank 3 and bank 4. Question?
If they do access the same bank,
you still have to wait. That will still be a structural hazard.
so it has to be serialized.
They have to be serialized. They have to be, yeah, if it's the same bank, they have to be serialized. Yeah. So that's another thing that we have done in optimizing the pipeline. So now you can imagine, okay, you can also have a pipeline in your memory. Question?
Memory write and read. Can we do the read and write simultaneously or not?
Say again?
So can we read the memory at the same time with the writing to the memory?
When you say read and write at the same time, at the same time, what does that mean?
So like
The same address or
not same address, just different address.
different addresses?
Yeah.
So it depends on if it's the same bank or not. If they are the same bank, no, you can. If they are different banks, yes, you can. Okay? All right. So right now, we can pipeline the memory, right? However, that also causes a problem. What if because right now your memory instructions are apparently having longer latency than other, right? And if that's the case, it's possibly that one memory instruction would want to write back, and the other instruction also want to write back at the same time. We cause another structural hazard. So how to deal with that? So the later one has to stall, right? Or say we have to make every instruction equally long. You have to make every instruction equally long so that all of them would be offset by a cycle when you write back. Okay, so now, based on what you have learned, go back to this very beginning question. Do you have an idea why instruction count matters and the CPI doesn't matter? Do you have any idea regarding that?
Because even though the multiplication instruction may take longer, it's being pipelined. So after the first so many executions, we're pumping them out at 1 per cycle anyways, because it's being pipelined.
Okay, so that's a very good answer, right? So here's the thing. If this is a pipeline processor, right, thinking about the fact that like from the last slide, you probably should know the performance of the code is probably not determined by the instruction, the single instruction speed, right? But by your slowest instruction. So in the previous pipeline case, that was the memory, right? But for here, it's apparently this modulation. So every pipeline is aligned with the speed of the modulation. And if you have more instructions, you have to wait for more cycles for them to output, right? So because the amount of modulation you have on both sides, they are the same. That controls your speed. So no matter how many instructions here, they are still going to be like, they still have to wait this to complete before they can go on. So when we count a CPI, right, that's a good question, right? The CPI is a synthesized value, right? So it takes longer time but more instructions. That's how you get lower CPI. Slightly more time but lower instructions, more instructions, right? So it doesn't mean that each instruction is longer or shorter. It's just because you have more instructions, so that's how you see that CPI goes lower, right? So that's why for these cases, your execution time is pretty much determined by the modular. And if you have more instructions in the middle, you have to wait them to output before you can perform the next modular. That's why instruction count actually matters, right? Because you have the pipeline processor. Okay, but for more detail about why this would determine the whole thing, we will have more detailed analysis after the midterm. So I know you are here for a reason, right? So today we are going to talk a little bit about the sample midterm. So first of all, the midterm I have printed is already handed to the TA, and we will have 15 multiple choice questions, which the format you are pretty much familiar with because I think the most questions that you have practiced in a class or in a grade scope is definitely multiple choice. So we have 15 of them, and we have assignment style free answer questions for 70%. So definitely you need to review your assignments, and closed note, closed book, no outside materials are allowed. And so like this is like the sample multiple choice questions, and you know, like those questions you look familiar, they look familiar because they are all from the slide. And remind yourself, right? Apparently, I'm not going to give you exactly the same question as what we have on the slide. So what I just want you to feel the style of the midterm and also remind you what are the key things, right? But a few things you have to remind yourself. What are the limitations of compiler optimizations? What is MLOS law? Remember that. Define the CPU performance equation and make sure that you can explain each term in detail. And like what would affect the performance equation, and what's the difference between latency and throughput? And what is benchmark suite? Why are they important? And why we say like T-flops or IPS is not a good metrics, right? And also for performance equation, you practiced this before, like for this code snippet, if we set a counter number to a certain, how much time it would take, right? How to calculate the speed up, right? And also performance on the code. So this is not on the slide, but in your homework, right? And also, if we change the arc and the size, how does that affect your cache miss rate, and what's the majority type of cache misses, right? And also practice MDOS law. So advertisement, we have CN Tech Talk tomorrow, 1 p.m. at Burns A265. We do provide pizza, so if you're hungry tomorrow, just wait for an hour after the CS seminar. You will get free food and also potential opportunities in job employment. And announcement, we would have assignment 3 due tonight, programming assignment 2 due next Tuesday, reading quiz 6 due next Thursday. Assignment 2 due next Thursday. Reading quiz 6 due next Thursday. All questions are sample midterm up from your homework or from the slides. So I sometimes feel like, you know, people ask, where can I find a solution? You know, that's a way what I want to do to force you review all the slides and midterm next Tuesday. Other than that, enjoy the rest of your day. Enjoy your weekend. Don't drink too much. Don't party too much. See you next week.
My midterm on Wednesday, flight